Okay, so this second video is in continuation of section 5.2, part 2, notes and examples. It says beyond example 6, use the graph of g, which is this function here, and areas to find the value of the definite integral. So in number 7, it's negative 1 to 2 of g at x dx. So in the first 6, what we did was we graphed the function in the integrand, found the area of that graph, and that was the value of the definite integral. Well, this time the function in the integrand is graphed over here, so there's nothing for us to graph now. The graph is given to us. So we want to calculate the area from negative 1 to 2, which is from here to here. Negative 1 to 2. We want to calculate the area from negative 1 to 2 under g bounded by the x-axis. So that would be all of this region right here. So that area is of a trapezoid, so it's 1/2 times the height. These are my parallel bases this time. So the height is 2 units high, and the base here is 1 unit, and the base here is 1, 2, 3. So that's 4. These 2's drop out, so that answer would then be 4. So the value of the definite integral from negative 1 to 2 of g at x dx would be 4. Also, because of, on your paper, each block is worth 1 unit. The area of each block is 1 times 1, or 1, and you can basically also count blocks sometimes to get the area. But that's not always the case. You're not always given blocks in which you can count the areas. Remember, any area above the x-axis is positive, and anything below is negative. Number 8, the definite integral from 2 to 3 of g at x dx means I want to calculate the area from 2 to 3 bounded by the x-axis. That would be from here to here. So since all that lies below underneath the x-axis, it would be negative. That result is of a triangle, so the area of the triangle is 1/2. The base is 1 unit long, from here to here is 1, and the height is 1, but because it's below the x-axis, it's negative 1. So that would be then negative 1/2 as that area. In number 9, we want the value of the definite integral from 2 to 4 of g at x dx. Well, that's from here to here. So notice what we have going on here is we have a portion below the x-axis and a portion above the x-axis. Anytime you have a graph that's part of it's below and a part of it is above, you have to find the area of each part. That is the area underneath, and then you have to find the area above and add them. So anytime the graph passes over the x-axis, you have to split up the definite integral there. So what I can do is I can go from 2 to 3. That's about 3.5, but to be sure I'll go from 2 to 3. Or I can go from 3 to 3.5. So 2 to 3 of g at x dx plus 3 to 3.5 of g at x dx plus, then I'm going to go from 3.5 to 4 of g at x dx. And I'm using here a very obvious property. The definite integral from a to b of, say, f at x dx plus the definite integral from b to c of f of x dx would be equal to what? Well, the area from a to b plus the area from b to c would give me the area from a to c of f of x dx. So that's what I'm doing right here. I'm breaking up the definite integral into pieces, and I'm adding their resulting areas. And the most important part is you have to break it up where it passes through the x-axis. You could do this area all in one shot. I could have gone from 2 to 3.5. but I'm going to use a little strategy here. From 2 to 3, I know that this area already is the area of a triangle. So this part here is 1/2 times the base, which is 1, times the height, which is -1. The height's -1, the base is 1. Plus, if you look right here, from 3 to 3.5, it would be a negative area. And it's just here 1/2, and from 3 to 3.5 is a half a unit long, and the height is -1. But if you look from here now, from 3.5 to 4, you have now the base is 1/2 unit long. The height is 1 times a half. So what you would get here is -1/4 plus 1/4. These areas would just drop out to leave it 0. We got the same area below the x-axis as we got above. So these two areas would just drop out. So the overall answer here to this, with these dropping out, would just be -1/2. And number 10, now we have a number 10. The definite integral from -1 to 4 of the absolute value of g at x dx. What this means to do is, think about it, the absolute value of g at x. It's going to take all these y's that are negative and flip them up. So it's the same thing as saying that any areas that are negative will now become positive, because the y's that were negative down here would now become positive. They'd get flipped up. So I believe this is the point 3, -1. It would be now become 3, 1. And the graph of it would look like this, at least this portion right here. It would just be flipped up. So the value of this would be the definite integral from, -1 to 2 of g at x dx, plus the definite integral from 2 to 3.5 of g at x dx, plus the definite integral from 3.5 to 4 of g at x dx. And I believe this first one we found is the area of a trapezoid. That was in the first example. This was a value of 4. And then from 2 to 3.5, just this part right here, from 2 to 3.5. So that's going to be area of a triangle, which is 1/2, times the base, which is 1.5, so that's 3 halves. 1 unit plus a half is 3 halves, and the height is 1. Plus 3.5 to 4, it's the area of a triangle, 1/2 times the base, which is a half, times the height, which is 1. So I believe we'd end up here with 4 plus 3/4 plus 1/4. 3/4 and 1/4 is 4/4, or 1 plus 4 is then 5. So again, just to make sure that everyone would understand this, that it takes the y's that are negative and would make them positive, but what that does graphically is it flips anything that's below the x-axis where the y's are negative now above the x-axis where the y's are positive. So all those negative areas will now become positive. And number 11, use the Math 9 feature on your 83 to calculate the value of the definite integral. So in number 11, you would do Math 9, and the function would be e to the negative x squared, comma x, comma 0, comma 5, and that would come out to be 0.886. In number 12, it says to find the calories burned by a walker burning 300 calories per hour from 6 p.m. to 7:30 p.m. And the directions said to write and evaluate a definite integral to find the desired quantity. So we have a walker burning 300 calories per hour. What definite integral can we write to find the answer of how many calories the person burned? So this is a rate. It's like given velocity, miles per hour. So the way we can get back to miles is to take its antiderivative. So we can get back to calories by taking the antiderivative of the function, which is of a constant. 300 calories per hour. Time is measured in hours, so we can just call it dx. So the time is measured in hours. So the definite integral is not going to go from, I guess you could do that. You could do from 6 to 7.5. You can't go from 6 to 7:30. That would not make sense. Or you can go from 0 to 1.5, because this right here needs to be in hours. So this here is measured in calories per hour. This here is measured in hours. These units drop out, which means the units are calories. Why are you multiplying these? Well, this is of a constant function. Its graph would be up here at 300, from 0 to 1.5. So that is from here to here. From here to here is a rectangle. And the area of that rectangle is the base, which is 1.5, times the height, which is 300. So that's why we multiply these right here, is that this right here represents the area of the rectangle. I'm multiplying this by this. This right here, dx, is the change in my x's, which is 1.5. And the height here being 300. So then, of course, if I multiply these to get the area, I multiply their units respectively to get the units for my answer. So the units of the 300 are calories per hour. The time is measured in hours. These drop out, and my answers are in calories. So it's going to be then simply the constant 300 times the upper limit minus 0. So 300 times 1.5 would give me 450 calories burned. Or I could have also gone from 6 to 7:30, which is 7.5. And still that difference is 1.5 hours. Okay, that concludes part 2.